Today our speaker is Dr. Joseph Romano, and he's in the Department of Physics and Astronomy. He received his bachelor's degree in electrical engineering from Cornell, and then his master's and PhD in physics from Syracuse University. Unlike the title suggests, his actual research interests are in gravitational wave data analysis, with specialization to the detection of stochastic background of gravitational radiation using data from ground-based or space-based interferometers or pulsar timing arrays. I'm sure if you're interested, he'll be happy to explain the details of that in a separate discussion. He's a co-chair of the LIGO Scientific Collaboration Stochastic Sources Analysis Group, and he was from 2000 to 2006 and is again currently. He has prior research experience in fundamental problems in both classical and quantum gravity. But today he's going to talk about the relationship between M.C. Escher and mathematics. So, Dr. Romano.
Thank you for the introduction and for giving me the opportunity to speak today. Just very briefly, how many here are science types? Okay, how many are from arts and humanities? Okay, so a little more science than art. But this is meant to be a fun talk with lots of interaction, so please ask questions during the talk, don't wait till the very end. Okay, I prefer things that way. So probably the hardest thing when giving a talk about M.C. Escher is to choose what topic to talk about. And there are many topics related to mathematics that one could choose, from things like projective geometry, topology and knots, representations of infinity, etc. But given that I only have an hour, I'm just going to focus on one of these, which is symmetry in the context of what are called periodic tilings of a plane. So the plan today is to give you a brief biography of Escher, then spend most of the time talking about symmetry transformation, again in the context of periodic tilings of the plane, and then discuss periodic tilings using regular polygons, but not just for flat surfaces, but for curved surfaces as well. So that's the goal. So biography, MC stands for Maurice Cornelius. He was born in 1898 and died in 1972 at the age of 73. He was a Dutch graphic artist doing woodcuts and lithographs. So he didn't do oil painting or charcoal drawings. I think you're familiar with woodcuts. This is an example. This is a self-portrait in sort of cut out from wood. Lithographs are basically etchings in stone. Okay, woodcuts and lithographs are very non-forgiving. Okay, so if you chip away a piece of stone, you can't just easily put that back on. Okay. Escher was inspired by visits that he made to the Alhambra in Granada, Spain, both in 1922 and 1936. And from 1937 onward, he was basically obsessed with this idea of periodic tilings in the plane, which in his words was his richest source of inspiration. Now, he was not a mathematician. I think he actually failed high school math or did very poorly in math at that level. But he thought like a mathematician. He was very systematic in the way that he went about things. And he corresponded with this mathematician, crystallographer Coxeter, and this mathematician, physicist Roger Penrose, which some of you might know. Okay, so here's a photo of the Alhambra in Granada, Spain. It was originally built by the Moors as a fortress in 889 and then subsequently converted to a palace in 1333. It's most known for its decorative wall tilings, which would be in the back here, which you can't see in this particular photo. Here are three examples, three different wall tilings from something very simple, which are white and black chevron or kite-shaped objects, sort of periodic, repeated patterns. Here's one a little bit more complicated, three-prong propeller pattern, six-pointed stars with lots of color. And then here, probably the most complicated of the three, you've got 6 pointed stars, you've got 8 pointed stars, 12 pointed stars, hexagons, lots of geometric shapes in this rather aesthetic pattern. Now here are some of Escher's sketches, which he made in 1936, his second visit there. And if you look closely, I don't know if you could see if the contrast is good enough, but these are sketches that he did on graph paper. You can actually see the lines here. And he was very meticulous and systematic, even in his sketches that he made. And this is sort of a characteristic of Escher's work, as we'll see. Some basic observations. The Alhambra wall tilings that I showed you are examples of what are called periodic tilings of the plane. So they're complete coverings of a flat two-dimensional surface like the wall or a floor using repeated congruent figures. And by congruent, I mean the same shape and the same size. This pattern, you can't have any overlaps or gaps, okay, when you create this periodic tiling. Now, instead of the geometric shapes, the hexagons, the triangles, the squares that the Moors used, Escher wanted to use recognizable figures in his periodic tilings, and you'll see birds, fish, and lizards used as the shapes. The fact that one uses congruent figures, which, as I mentioned earlier, have the same size and shape, limits the allowed transformations that you can do for a periodic tiling to just 4 things: translations, rotations, reflections, and glide reflections. Now, out of curiosity, how many have heard of translation, rotation, reflection, glide reflection? Anybody heard of glide reflection? Okay. I never heard about it until I started learning about Escher and his periodic tilings. And then just by way of definition, when I say that something, or when somebody says that something is symmetric with respect to a particular transformation, what that means is that it's unchanged it's unchanged after you apply that transformation. So the way that something looks before and after you apply the transformation are identical. That's what it means to be symmetric. Okay, so now let's get into the main part, symmetry transformations. And I'm going to do this in the context of Escher's prints. So everything that I'm going to show from here on out are prints of Escher's. This is a print with birds, black birds and white birds, different shapes. We're going to ignore color in everything that we look at, just because it will simplify things, okay? Here you can tell the birds are different even if they weren't colored, okay? Just from the different shapes. Now this is an example of a periodic tiling that only has translational symmetry. And by translational symmetry, that means if you slide the figure in this direction, say from this point here up to this point, so the eye of the white bird to the eye of the white bird, it repeats. You map the image back to itself under this translation here. And similarly, if we go up from this eye here to that eye here, it repeats. You have to imagine the print extending off to infinity, both horizontally and vertically, but this is what I mean by a translational symmetry. And all periodic tilings have this translational symmetry. Here's an example of a print that has, in addition to the translational symmetry shown by the arrows, rotational symmetry. And there are 3 different types of rotational symmetry defined by the angle through which you need to rotate the figure in order to map it back to itself. So for example, if you look at this point here, this is a so-called center of threefold rotational symmetry, okay? There are 3 wings meeting at this dot here. So if you rotate the figure by 120 degrees, which is 360 divided by 3, you map the image back to itself, again, ignoring the color, okay? The color of the butterflies. This is a center of twofold rotational symmetry. Rotate by 180 degrees, you map the image back to itself. And this dot here is a center of 6-fold rotational symmetry, which means that if I rotate by 60 degrees, this wing maps to this wing maps to this wing, etc. Okay? Any problems with this? Any questions? Remember, you can interrupt or ask anything at any time. Here's an example of a print that has, in addition to translational symmetry, reflection symmetry, or sometimes called mirror symmetry, which basically means that the image is the same if you reflect across this axis here. Okay? Human beings, for example, are approximately mirror symmetric, or have this reflection symmetry about an axis passing through the center of your body like that. Okay? And finally, our fourth symmetry transformation is this thing called a glide reflection symmetry, which is actually a combination of two things: a reflection followed by a translation. Okay? So these three dotted lines here are axes of glide reflection symmetry. And I want to illustrate that with this little mock-up here. So pay attention to this dog. Okay? What we're going to do is we're going to reflect the dog around the axis and then translate it up. Okay? And when you do that, this dog maps to that dog. And the whole image maps to itself. Okay? So that's called glide reflection. Reflection followed by a translation. Okay? So that's about the hind legs. I could do the same thing about an axis passing through the jaw of the dog. Okay? So we concentrate on this dog now. You reflect, and then you translate up, and then this dog maps to that. And similarly, if you ignore color, you can consider the axis that passes through the front legs of the dog. Again, you reflect and you translate up, and then this dog maps to that dog. Okay? Again, because we're ignoring color, right? These are the same under that symmetry transformation. Okay. Now, everybody's been quiet. I don't know if that means that everybody understands things. So this is a test. Okay? So this is a test print which has all the four symmetries: translation, rotation, reflection, and glide reflection. So I want you to tell me, if I start at this point, where do the translation arrows go to? Where do I map this point to in order to have translational symmetry?
Looks like you have rotation there.
Well, we do have rotation there, but let's just start with translation. Okay? So where do I take this point to? Do I take it up to here? Where do I map it to?
To the side.
To the side, 45 degrees? Or here?
Oh, that's opposite.
Okay, if you map it up to here, let's see, is that right? If I go from here up to, let's see, here up to
Yeah,
here,
that's right. Yeah.
that's a translational symmetry. Here over to here, translational symmetry. You see this angel becomes that angel. Okay, so those are the translational symmetry arrows or vectors, as they're sometimes called. What about rotation? You had mentioned rotation.
Looks like a 6.
Is it 6?
Fourfold. It's a
Four. Fourfold for the four wings. Okay. Is there any other centers of rotational symmetry? Or is that it?
Where their feet meet?
Where their feet meet. Okay, so where the feet of the angels and devils meet. What is this?
That's a C.
Looks one.
It's a 180.
It's a one-fold?
No, it's a twofold.
Two-fold. Okay, by 180. Okay, 180 I get here. Okay. So we've got fourfold, twofold. Okay, shown by those dots. What about reflection symmetry?
That's the
Everybody see the reflection symmetry? Through here and through here, right? Through the centers of the angels and the centers of the bats. What about glide reflection? This is tougher. You can think of glide reflection as sort of like footprints in the sand. You go right, left, right, left.
Then we can change
Yeah.
the position.
You could do that.
Okay, so I see you going sort of this way and up, okay? is, so you said there's an axis here. Okay, so if you look at that axis, so that turns out to be correct. Okay, because you reflect and then translate up, and then this angle maps to that. Okay, and similarly over here, you reflect and translate over, that angle maps to that one. There's also another axis of wide reflection symmetry, which is harder to see. Any ideas what that might be? Jessica, you seem to have
Maybe diagonally?
diagonally. Yes, there is a diagonal
I'm trying to figure it
axis.
out, but I can.
Okay, it's
I
very,
think
very
it's
hard
there.
to see, okay?
Right.
Okay, so here, let's try to illustrate that with this, okay? So look at this line here, that dotted blue line, and consider that angel, okay? Reflect and translate. Okay, so this angel maps to that angel. Okay, you see that? So you start like this, you reflect, and then you go up.
So, why is that different than the rotation?
It's not a rotation. I mean, you can't rotate around a single point to map this angel up to here.
But that's not the floor.
Right, so this fourfold rotational symmetry, where is it? Here,
Yeah,
just maps one angel.
is that angel?
You're correct. Yes, this angel does map to that angel under a fourfold, under a rotational symmetry. Right? Fourfold rotational symmetry. Yes, you might be right. I mean, it's doing the same thing.
So
You're correct. I didn't appreciate that until now. Okay. Okay. Well, anyway, I mean, this is a glide reflection symmetry that does the same thing as a fourfold rotational symmetry for that particular case. Thank you for pointing that out. Okay. Here's a print of Escher's that basically shows you his thought process in creating these these prints with recognizable figures. He starts off with something very simple, a lattice of parallelograms, okay, and then he takes those parallelograms and he deforms them, in a very particular way, where he takes a little bit out of one side and puts it on, sort of moves it over to the other side of the parallelogram, from here to here, and then also from here to here. And by doing that, he's basically preserving the area of each of the parallelograms, okay? So you see how he's doing that here. And then all he's doing to go from here to here is he's exaggerating the deformation. Again, whatever he takes off this left side, he puts on the right side. Whatever he takes up from the top here, he puts on the bottom there, okay? And then it's his artistic genius, which basically says that these deformations actually look like birds, okay? And they look like birds just by putting in this sort of these interior lines that make these shapes here look like birds. And these are red birds flying to the right on a white background, okay? But now he just takes the white background, puts some interior lines on those, and those are actually white birds flying on a red background. Okay? And then he puts interior lines on both, and you've got red birds and white birds flying to the right together. So he's playing with our perception of what is figure, what is ground.
So
Yes?
the numbers on there, are we supposed to read it 1, 2, 3, and so on?
Well, I mean, it's basically, so this is just a single print of Escher's, but it's basically showing his thought process in going, from a blank sheet of paper, so to speak, to something more complicated. So he's deforming the parallelograms, deforming them a little bit more. Now they have their final shape. Now he puts some interior markings on some of those shapes so that they look like red birds. puts the interior markings on the white shape, so those look like white birds. Now you've got white birds and red birds. And then he says, well, maybe those aren't birds after all. Change the interior markings and they look like fish, flying fish or something like that, going to the left instead of birds flying to the right. And then he says, well, let's keep the white fish as white fish and change the red fish to red birds flying now to the right. Okay? So this is Escher, okay? Doing something, you know, to play with our perception. Okay. Now, it turns out that constructing periodic tilings using these asymmetric figures can be done in multiple ways. Okay? You don't just have to take these parallelograms and deform them in the way that I showed you previously. Okay? Here is a print of Escher's with seahorses. And if you look, again, the basic or fundamental unit is a parallelogram. But now what he does is he takes off something from, say, this side and maps it over there, like we saw before. But now to relate these two sides here, it's not a translation. You're not taking something off here and putting it over here. You're actually rotating this shape into that shape there. Okay? So that's another way of forming a single asymmetric tile, which you can then use to completely tile the plane. Okay? And it turns out that there are 28 different ways of constructing such asymmetric tiles. This was proved by a mathematician, Heinrich Heesch, and it's called the Heesch group. Okay? And Escher remarkably came up with 27 of those on his own, independently of Heesch. Okay? So Escher's work with periodic tilings basically predated some of the work by crystallographers and mathematicians at the time. Okay, so now let's go simplify a little bit in the sense of not considering asymmetric tiles, but we're going to consider periodic tilings using regular polygons. And by regular polygon, I mean shapes, okay, that have equal length sides and equal opening angles, okay, like squares or equilateral triangles, for example. Okay, so I'm going to ask you a question, okay, and I need a response. How many ways can you tile a two-dimensional flat space like the wall or the floor using regular polygons? 0 ways, 3 ways, 5 ways, infinite number of ways. And maybe you can think of what you saw when you came into the building or in some other building on campus or in your house. What are the ways that you can do this? Infinite? Well, it's infinite if you define it in a certain sense, but let's not include infinity, okay? I mean, it's I don't know if the infinity you're thinking about is the same infinity that I'm thinking about. Okay?
But if you made an infinite polygon, wouldn't that be a circle? And so circles wouldn't do it.
No, you can't tile the plane with circles, right? I mean, so when you say infinite, do you mean that there are an infinite number of polygons that you can use?
Maybe 5.
Maybe 5. Any other? Can you just name some? What about, what type of triangle?
Equilateral.
Equilateral triangles, okay? So you can tile the plane with equilateral triangles, okay? Now when you put enough equilateral triangles together, what other shape can you get?
Squares.
Square, rectangle.
Not squares, but...
We get the parallelogram.
Parallel.
No, but for remember, equilateral triangles have
equilateral,
60-degree angles. So you can't get a square by putting
Rectangle.
hexagons.
So hexagon.
Okay, hexagons, okay, so that's the second way. And then squares, okay? Not general parallelograms because we're restricting now to regular polygons. So everything has to be equal length sides and equal interior angles. Okay?
So 3.
So the answer is 3. Okay, so that's it. Three ways, okay? And here's what they look like, okay? This is kitchen floor or something like that. Okay, square tiles. These are using equilateral triangles, and these are using hexagons. And the notation I'm going to use PQ. P stands for the polygon, the number of sides, so a three-sided polygon. And the 6 here corresponds to how many of those polygons meet at a vertex. So you've got 6 equilateral triangles meeting at each vertex here. You've got 4 squares meeting at each vertex. You have 3 hexagons meeting at each vertex. Now the infinity, you don't have to admit whether or not you were thinking of this. The thing that allows infinity is if you, say, slide this set here relative to the other, okay? Or you slide this, okay? If you weren't thinking of that, then your infinity was the wrong infinity, okay? Okay, but now let me ask you a slightly harder question. How do you prove, mathematically, that these are the only 3? There are 3 and only 3 ways of doing this. What do you do? What's the condition that you need in order to determine the type of polygon and how many of those meet at a vertex?
1 second.
Any ideas?
Well, you had the 4 restrictions on transformation, rotation. So if you're defining that it's a regular polygon,
Yes.
when you undergo those transformations, that they are unchanged, because that was the by depth. So what?
Well, yeah. So each of these have some set of symmetry transformations. So there's like 4-fold centers here. There's 6-fold centers here. There's 3-fold centers here. But there's something I think a little bit, I don't know if it's an easier way of thinking about it, not necessarily in terms of symmetry transformations, but something in terms of angles.
Visible to 360.
360, okay, the angles here, so when you sum around each vertex, you have to get 360 degrees, regardless of if you're talking about 3 of these hexagons, or 4 of these squares, or 6 of these equilateral triangles. The sum of the angles there equals 360, okay? So that's the answer. The sum of the angles around each vertex is 360. But now to connect that to, the allowed values of P and Q, you need to know what the opening angle is for a p-sided polygon, okay? So for a 3-sided polygon, it's 60, then 90. 5-sided, it's 72? No.
Yep.
Okay. There's a formula, okay, that you can write down. Basically, I wish is there a board here or something?
Yeah, those open up too.
Okay. I've got markers.
Watch your face.
So the idea is this, suppose we have a pentagon. Okay, and we want to know what the opening angle is here. Okay? The way that I remember how to do it is I divide it up into triangles. Okay? Into 3 triangles. Each triangle has 180 degrees. So 3 times, so I take 3 times 180, right? And then I divide by the number of vertices here. Okay, and whatever that happens to be, 3 times 180, so 0, 4, you carry the 2, 540, divided by 5.
108.
108, okay? 108 degrees, okay? Now in general, you can do this for a p-sided polygon. You would have p minus 2 times 180 degrees. Okay, so you divide your p-sided polygon into p minus 2 triangles, each with 180 degrees. Divide by p. That gives you the value of an interior angle for a p-sided polygon. Okay, regular polygon. Now we want the sum of the angles around each vertex to equal 360, so we need to multiply this by q, because we have q of them meeting at each vertex, and that has to equal 360 degrees. Okay? And assuming that most of you are science types, if we divide by 180 degrees each side, and we move the q over here, we get p minus 2 over p is equal to 2 over q, which is 1 minus 2 over p equals 2 over q, or 1 over p plus 1 over q equals to a half. Okay? So this is the condition that must be satisfied in order for you to have a tiling of the plane using regular polygons, q of those meeting at each vertex. Have any of you seen this formula before? Okay, it's a nice formula. I mean, I didn't see it until, you know, very late in life, but it's a very nice, simple formula. And if you check, 1 over 3 plus 1 over 6 is a half. 1 over 4 plus 1 over 4 is a half. 1 over 6 plus 1 over 3 is a half. Okay, so that's that. Okay, so I just walking through the steps there that I wrote on the board. Okay, so this is the condition. Okay. Okay, so now we're going to make life a little more complicated. Okay, we're going to consider not just tiling a flat surface like the floor or the wall, but we're going to consider curved surfaces like the surface of a basketball, a 2D sphere, or the surface of a saddle. Okay? Okay? This surface has what's called positive curvature. This surface here has negative curvature, and this has zero curvature or flat. Okay? This is so-called Euclidean space and obeys Euclidean geometry. It's the geometry that one learns in high school. And the most important property of these spaces is this, is that if you sum the angles of a triangle, any triangle that you draw on a flat surface, you get 180 degrees. But if you do it on a sphere, you get something greater than 180 degrees. And if you draw it on a saddle surface, so something with negative curvature, you get less than 180 degrees. Okay? So these are the properties that I'm going to remember as we go forward. Okay? And note that you can draw, or you can talk about straight lines even in a curved space. Okay? Straight lines in a curved space are the lines that have the shortest distance between 2 points. So on the surface of a sphere, the straightest lines are arcs of great circles. Okay? So we can talk about straight lines, and hence we can talk about polygons, regular polygons drawn on a spherical surface, or drawn on a surface with negative curvature. Okay? So now let me ask the question, how many ways can you tile a two-dimensional sphere using regular polygons? Okay? And let me just sort of give you sort of an example. So you imagine the sphere, oops, like this. Okay? Now I can go from the North Pole and I can go along an arc of a great circle down to the equator. I can go over, you know, a quarter of the way around, and then I can come back down. These angles here are all 90 degrees. So I've formed a triangle 90, 90, 90, so 270. But this is an equilateral triangle, if you will, on the surface of a sphere. Okay, so using such triangles or using such polygons constructed that way, how many ways can I do it? You didn't expect to be given a math test today. Any guesses?
Zero.
Zero. Okay, but can I construct something using those?
It looks like it, yeah, that's so, you've got, if you're starting from the pole, right?
Yeah, starting
And
from the pole.
And if it's
I'm starting from the pole and I'm going down, so I'm starting here at the pole, I'm going down to the equator,
yeah,
okay? Then I'm going around on the equator, over to here, and then back up to the pole.
so at least one.
Okay, so that one, so you'd have one here, one here, one here, one here. So eight such
Yeah.
triangles will give you a tiling of the sphere. So there's at least one.
So we know we're going to 3 because there's no 1, so at least we're going to 3.
Okay, so.
And we're not going
Yeah,
to
right.
infinity,
So
right?
zero's wrong, okay, so we got a good test taker over there, okay? It's gotta be at least this, or this.
I'm gonna go for 3 again.
Go for
Yeah.
3.
Does it really matter whether it's elliptical or hyperbolic?
Yes, it does.
Okay. Carmadium.
This is somewhat of a trick question,
Oh, man.
just for those who thought the talk was too easy.
What's a 2D sphere?
2D, this is, so by two-dimensional,
Definition.
so in mathematics you can construct spheres in 3 dimensions and 4 dimensions and n dimensions. So sphere, when I'm talking about a 2-dimensional sphere, I mean the ordinary surface of a basketball, for example. So it's a 2-dimensional surface.
If you're on the surface.
So it's hollow, it's not a solid, not a solid.
We're not,
object.
we're just talking about the surface, not the solid, the 3-dimensional solid.
Yeah. So you're on the surface, it's 2D because you're...
It's 2D on the surface, latitude and longitude, for example. Well, let me just sort of take the suspense away, okay? The answer is 5 or infinity. I said it was a trick question, okay? And let me show you these, okay? Oh, and I should say that one shouldn't have to guess.
Oh, right.
We should be able to write down a tiling condition for the sphere with positive curvature in the same way that we did for flat 2-dimensional space. The only difference now is that when you sum around the vertex, again, you still have to get 360 degrees. But now the sum of the angles of a triangle, for example, we said is greater than 180 degrees, not equal to 180 degrees. So this 180 degrees here needs to be replaced by some number greater than 180 degrees, okay? And if you go through the same construction, replacing this 180 by something greater than 180, this condition here changes from 1 over p plus 1 over q equal to half to 1 over p plus 1 over q is greater than a half, okay? And then you ask, what are the values of p and q such that when you form that sum, you get something greater than a half, and you find that these are the values. 3 and 3, a third plus a third is 2/3. Right? A fourth plus a third is greater than a half. A third plus a fourth is greater than a half. 5 and 3, 3 and 5, and then 2n and n2. Okay? This is where the infinity comes. The infinity comes from here. These are the 5 sort of normal tilings. Remember, P stands for the number of sides of your polygon. This is a 2-sided polygon. How can you get a 2-sided polygon? Right, if I did a 2-sided figure on the wall, what's a 2-sided figure on the wall? It's a line, there's nothing. Yes, but on the sphere, as, what's your name?
It's an
Ross, as Ross was saying, you can draw sort of something from the North Pole all the way down, okay, like a wedge of an orange, okay? So imagine a beach ball, okay? So those are 2-sided figures, and you can make the angle here as big or as small as you want, and hence you can get n of those going around the sphere. This is an n-sided figure meeting 2 at a vertex, which is kind of weird. Any idea how to do that? If you only have two of these polygons meeting at a vertex. That's a weird shape. Do you have that? It's half the basketball.
Right.
So you take the basketball, that's right, you take the equator on the basketball, okay? And then you draw n equally spaced dots. Okay, here's one dot, here's another dot, here's another dot. That's the n-sided figure. The n-sided figure. So that's the vertex, if you will, of your polygon, okay? So very good, that's a hard one.
So I have a question, if you go back.
That's this,
So
yes.
if you go back to the equation,
yes.
so I figured that it was greater than a half and it would be less than a half for the hyperbolic surface. But if n is equal to infinity, then that equality never works, right?
Oh, infinite. No, you're right, but you can't take n to
So you can't have a
infinity, but
continuous-
n can be arbitrarily large.
Yeah, it can be, yeah, but it can't be infinite, you can't have a
It
continuous.
can't, no, you can't have infinity of those.
Right,
Right,
okay.
but n can be arbitrarily
That's why I got
large.
stuck.
Okay, very good. Okay, so these are the so-called degenerate tessellations, the ones that give you, right, the beach ball and the n-sided figure, okay? And then these are the other ones, the 3-3, the 4-3, 3-4, okay? Yes?
So is the 5-3 really a soccer ball?
Well,
Like
a
say-
soccer ball actually has hexagons as well.
Yeah,
Okay.
okay, so it doesn't satisfy the conditions.
Well, the soccer ball is different than this because the soccer ball is made up of two types of polygons.
Right, they all have to
Okay?
be.
Here we're talking about a single polygon, okay? Now, the question is what do these tilings correspond to if you effectively remove the sphere? If I sort of take the sphere away, the underlying sphere, and I pull those lines taut, make them straight, this would be a set of triangles sort of meeting, okay, which looks like this. What do you get for this one?
Cube?
Cube. Very good. What do you get for that other one?
Which other one?
This one here.
Oh.
So they're triangles.
Right. Pyramid?
Two-sided one.
Two-sided period. Okay. That's
So
an
square-
octahedron.
Square by pyramid.
The thing that looks like a soccer ball is actually a dodecahedron. And this 3-5 tiling is an icosahedron. Do you know what these things are called?
Platonic solid.
Platonic solids. These are the so-called platonic solids, the 5 platonic solids made from regular polygons. Which I found, I mean, that blew my mind, I guess, to know that the tilings on the surface of the sphere, at least these, you know, these non-degenerate ones, are actually the same as platonic solids. Okay, and here is Escher's rendition of angels and devils on the surface of a sphere. Okay, and he's basically using the squares or the regular quadrilaterals meeting 3 at a vertex, the cube tiling. Okay, so now here is the last example. It's the hardest one, I think, to get your head around. And this is for a two-dimensional hyperbolic space. Yes?
I have a question on the last one. So with the symmetry transformations that you indicated in a flat plane, will they still apply to that?
I will get that. That will
Okay.
be my last slide.
Okay, all right.
Okay. So here we're moving. So we move from flat space to the surface of the sphere, positive curvature, now to a negatively curved space, so-called two-dimensional hyperbolic space. Now it turns out that I can't show you. Okay, I showed you a saddle surface. Okay. Now a saddle surface does have negative curvature, but that negative curvature changes as you move from point to point on the saddle. If you want a surface, a two-dimensional surface with constant negative curvature, it turns out that there's a mathematical theorem that says you cannot represent such a surface as an ordinary two-dimensional surface in three-dimensional space. Okay? So because I can't show such a surface, you have to represent it some other way. Okay? And this other way, this one particular way of representing it is using this thing called the Poincare disk model, which is very similar to, or analogous to, stereographic projection of a sphere. So I think you're familiar with maps, right, in an atlas that you get by taking the surface of the Earth and projecting somehow to construct your map on a flat surface. Stereographic projection of the northern hemisphere onto a disk is analogous to what's being done here. Okay, so this Poincare disk model or representation is a finite representation of a space which is actually infinite in extent. Okay, And infinity is represented by the boundary. Okay? So infinity in the two-dimensional hyperbolic space is represented in this model by the boundary of this disk. And straight lines in the hyperbolic space are represented by arcs of circles that meet the boundary at right angles. Okay? So these are the lines that we use to construct our polygons. Okay? So for example, I can construct a triangle using such arcs, and the sum of the angles of that particular triangle, or any triangle that I draw in this space, will be less than 180 degrees because it's a hyperbolic space. This representation is given the technical name conformal, a conformal representation, in the sense that angles are preserved. Angles measured in the abstract hyperbolic space are represented faithfully in this Poincare disk. Okay? But distances are distorted in the same way that distances are distorted for a stereographic projection. If you remember how maps look when you do the stereographic projection, the countries near the equator are distorted. They appear larger than they actually are relative to the other countries near the North Pole. Well, here, for the hyperbolic space, these figures, which all have the same size and same spacing in the abstract hyperbolic space, actually appear smaller and get closer together as you move toward the boundary. Okay? Okay. So the question now is, how many ways can you tile 2D hyperbolic space using regular polygons? So the same question that I asked for flat space in the sphere. And using your suggestion, right? I mean, we have a similar tiling condition for hyperbolic space, except the greater than sign should become a less than sign. Okay? And if you ask now, how many ways can you get 1 over p plus 1 over q less than a half, there are an infinite number of ways that you can do that. Okay? And if you basically represent this, the different types of tilings that you can do, the different values of p and q, you see that these 3 different spaces are complementary. Flat space, we have these 3 different ways, using hexagons, squares, or triangles. For the sphere, we have these corresponding to the 5 platonic solids, and then these degenerate cases corresponding to the beach ball and that other example. Okay, and hyperbolic space fills in everything else. Okay, and that's a representation of this mathematical tiling condition. So here's an example of a tiling of the Poincare disk using 45-45 triangles, okay, meeting 8 at a vertex, because you have to get 360 degrees at each vertex. Okay, and it's similar, if you will, to tiling a flat space using equilateral triangles. Okay, note that these triangles, even though they appear to get smaller and have different shapes, actually have the same size, shape, etc. in the abstract hyperbolic space. It's just the property of the sort of the projection onto the disk that you get this distortion as you move toward the boundary. Okay? Here's a very extreme example where the triangles have 0, 0, and 0 as the angles. Okay? So you know that the sum of the angles can be less than 180 degrees. Well, the sum of the angles can actually be 0 if you allow the triangles to extend all the way to infinity. Okay? And again, this big triangle here, and this other triangle here, and this triangle here, and that triangle there, they're all the same. They have all the same shape. Yes?
So if I kind of look at this, it's like a three-sided triangle in the middle. The next there's 6, the next there's 9. Is it sort of 3n in terms of how is it fractal is what I'm wondering.
I don't know if you would call this fractal, but Escher has done fractal prints.
Okay.
And he predated Mandelbrot and all those people doing fractal geometry. Yes. Okay, here's one of Escher's prints called Circle Limit 1, okay, which he did in 1958. And if you look at it, it's actually based on a tiling using hexagons, meeting 4 at a vertex, okay? So the fundamental cell, if you will, is this, and then it's just repeated, okay? In this hexagon, this hexagon, this hexagon, this hexagon, etc. Okay? Now, Escher didn't come up with this idea himself. He actually was inspired by this mathematician crystallographer Hoxeter, who sent Escher via ordinary mail, because they didn't have email at the time, a preprint of his from, I think, a math paper. You can read some of the text here, where this is a figure, okay? And so this is the Poincaré disk model, and it's a tiling using, you can see the hexagons there divided up into smaller triangles. Now, Escher did not know hyperbolic geometry. He could probably care less. Well, I don't know if he would care less about it, but he didn't need to know the abstract math. He was such a good draftsman that he was basically able to reconstruct the scaffolding, if you will, using, straight edge and compass. Okay, so this shows here a reconstruction of Escher's rebuilding of the scaffolding using straight edge and compass. This is Circle Limit 3, a year later after Circle Limit 1, and you can see, compared to the first Circle Limit print that Escher did, this is much more aesthetically appealing. The fish here are organic, they're rounded. There's a nice flow pattern from one boundary to the next. Okay? And that's based on a tiling using octagons, okay, not hexagons. And his fourth and last Circle Limit print is, again, using the theme of angels and devils, called Heaven and Hell here, where he's got basically, I think, the hexagon, right, the 6-4 tiling, using hexagons meeting 4 at a vertex, okay? So here are Escher's 3 different renditions of angels and devils on a flat 2-dimensional space, on a 2-dimensional sphere, and on 2-dimensional hyperbolic space represented using the Poincaré disk model, giving different sort of realizations of this 1 over p plus 1 over q greater than, less than, or equal to a half tiling condition. And getting back to the question that you asked, remember we talked about 4-fold and 2-fold rotational symmetry there. Note that this 4-fold rotational symmetry becomes 3-fold here, and you need it to be reduced in order for the space to curve around to form the surface of a sphere. Okay? Here, the 2-fold symmetry becomes 3-fold, and that's because this hyperbolic space is actually more infinite, if you will, than the infinite flat 2-dimensional space. So this is, I think, an answer to your question.
So it looks like, so this was a 6-4 on the right, but it's got 3-fold symmetry, and this is 4-fold, but it's got a 2-fold axis. So I'm wondering if it's n over 2, where n is given by the number of sides of the n-gon, in terms of the symmetry element in the center.
Oh, the rotational symmetry?
Yeah.
I don't know. I haven't thought of that.
I'll think of that.
Okay. So let me conclude then with some references and credits. If you're intrigued by any of this, there's a great online site called Escher Math, which I got a lot of the ideas from when producing or when making this talk. And there are a couple books which I have here. You can take a look. The Magic Mirror of M.C. Escher by Bruno Ernst. Bruno Ernst was a mathematician who interviewed Escher during the last 2 or 3 years of his life. So there's a lot of mathematical figures and discussion of Escher and math in this book. And then there's this other book by Doris Schatzschneider about Escher's symmetry drawings, or periodic tilings. Okay, so I highly recommend these books. Both of these are written by mathematicians, And there are a lot of other articles that you can find on the web as well. Okay, so I'll stop there, and I'll be happy to entertain more questions if you have them. Yes?
So I'm wondering if you wanted to try to teach kids about all of this. I mean, could you do it with cutouts?
Yes, yes, I think, I think Escher Math is aimed at high school or lower level students. And I think you can go online and you can buy Escher cutouts, you know, with dogs and things like that. I learned from reading some books about Escher and by Escher that when he would give talks, he basically had things like this. He had long pieces of wire and figures, you know, that you could slide on the wires to illustrate different transformations. But yes, this is something that can be brought, I think, to the classroom, definitely at the high school level, and probably less than that as well. My daughter, you know, many years ago, was learning in her high school math class about wide reflections, which I had never heard about, you know, until I was 50 years old or something, getting ready for this type of talk.
It'd be a good way to entice students to, so I'm a chemist, and so we have an interest in symmetry,
Yes.
obviously, and so it'd be a good way to get people interested in symmetry before you actually talk to them about group theory and some of the other
That's right.
crystallographic things, and space groups and point groups.
Yes.
So you said Escher wasn't a mathematician, so how did he think of these things? He was just, I mean, did he think about them in terms of symmetry? Did he think about them in terms of, you know, elementary geometry? I mean,
I don't know, honestly, how he thought about them. I mean, but he has notebooks, so in here, in this particular book, it shows you know, copies of some of Escher's notebooks, where he basically systematically categorizes the different types of ways that he can form these periodic tilings. So he was most interested in tilings of a flat space, okay? And he wanted to tile them using asymmetric tiles, okay? Sort of like those seahorses that I was showing. And the question that Escher had is, how many different ways could he do that? Okay, and he didn't want there to be any reflection symmetry because that, I don't know, wasn't appealing to Escher. So he was trying to come up in his notebook with the number of asymmetric tilings that you could use to tile flat two-dimensional space. As I mentioned, he came up with 27 of those, and he either before or after actually proved that there were 28 of these, which I thought was pretty amazing.
so that seahorse structure, actually, as you were showing that, I was thinking hexagonal closest packing, because that's exactly how you do it. Because it was A, B, C, and then it has to repeat in terms of that kind of formalism. So it was kind of interesting to see that, and it's something I could actually use as kind of.
Okay, I didn't know that it had what did you say, type of close packing?
Hexagonal closest packed.
Okay, because I thought that is based on,
So if you look, so the blue level, then there's a white level, and then a red level, and the blue level above that repeats the blue level below it. So it's an ABC kind of thing. And that's a hexagonal closest packing in terms of crystal.
okay, so even though this lattice here is this is a parallelogram, it's still a hexagonal close packing, okay?
So it's kind of there. So it's really. I'm just thinking about this as a cool way to sort of teach crystal structures for chemists. So.
Yeah. No, that's great. And you can take, instead of parallelograms here, other-sided, you know, six-sided figures. And again, the question is how do you relate the, you know, neighboring sockets?
Yeah. So this is like a two-dimensional representation of hexagonal closest packing is three-dimensional. So this would be sort of a cutaway through a two-dimensional representation.
Yes, that's right. And there's a lot of things that you can do in 2 dimensions that are simpler than sort of the 3-dimensional case, like the number of space groups. I think in 3 dimensions is what, 230 or.
Yeah.
I mean, if you ask how many ways can you fit things together in 3 dimensions according to their symmetry properties, I think there are 230 ways of doing that.
Right.
Whereas if you want to classify ways that you can tile the plane, two-dimensional surface, flat two-dimensional surface, there are 17 different ways. Again, if you classify them just by their symmetries. And this was actually proved by Polya and some other mathematician, Russian mathematician, Fedorov, in the late 1800s.
Yeah, the only sort of crystallographic transformation that he's missing, and you couldn't do it in 2 dimensions, is the screw axis. Otherwise, the glide planes, which we're talking about as the glide reflections, that can all be done in 2 dimensions, but if you add that one extra thing, then you can do what Escher's doing in 2 dimensions on a 3-dimensional surface, and it'd be kind of fun to look at that.
Yeah, and I think people have come up with sort of asymmetric 3-dimensional, right? So you know, for kids, you were saying about how you can get these like little cutouts and you can make, you know, mats of seahorses. But now you can do, I think, 3-dimensional, using 3-dimensional asymmetric figures as well,
Escher cubes.
which is pretty cool.
This is a dumb sort of artistic question. Does anybody ever, I mean, you could cut these out and you could set up your home tiling in these sort of things, right? Does anybody ever do that?
I suspect people do. I mean, I know that many years ago I went to some museum, I think in Baton Rouge, Louisiana, like a science museum. And in the, well, I don't know if there's a kid section in the museum because everybody's a kid, right? I think when you go to a science museum, they had, you know, these big, you know, they had these things where you sort of tile them. You know, they were like rubber tiles that you could use for big spaces.
Well, thank you so much.
Okay.
We
You're welcome.
appreciate it.
Thank you.